In this video, we're going to be learning a number of strategies that can help to balance some of the trickier types of chemical reactions, starting with what we call the major OH, or major hydroxide strategy. This strategy is used when you're given a chemical reaction that has oxygen or hydrogen in multiple locations, such as this first reaction here, because it's quite difficult to figure out where to actually start balancing. Well, if we use the major hydroxide strategy, this simply states that we need to balance what we call the major atoms, that being any atom other than oxygen or hydrogen, before tackling oxygen and hydrogen. In this case, there is only one major element, phosphorus. There are 4 phosphorus atoms in the second reactant here, and only one in the product here, meaning that we can simply add a balancing coefficient of 4 in order to balance phosphorus. Next, I would recommend balancing hydrogen before oxygen, at least in this reaction, because hydrogen can only be found in a single reactant here. So we can see, because of our balancing coefficient of 4, 4 times 3 is a total of 12 hydrogen, so we can put a 6 coefficient here, because 6 times 2 is a total of 12 hydrogen. Now at this point, you might get lucky and oxygen might actually work itself out after the major atoms and hydrogen have been balanced, and that's exactly what we see here. 4 times 4 is 16 oxygen that we see in the products. Then we have 10 oxygen in our second reactant here, and because of the balancing coefficient of 6, we have 6 oxygen here. 10 plus 6 is 16, so oxygen has balanced itself out here. Now in our second reaction, we can actually start the same way by balancing the major non-hydrogen and non-oxygen elements, of which the main one is the metal titanium. So we can see that there are 3 titanium in the product side, and we can add a balancing coefficient of 3 to balance out titanium on the reactant side. Now at this point, we get a little bit overwhelmed because again, we see that hydrogen and oxygen are found in multiple locations. Now here, what we can do is we can look at the polyatomic ions that are present. So here we can see that hydroxide is present in our first reactant, and the polyatomic ion phosphate is present in the second reactant here. Now, what we can do here is group all of the atoms within polyatomic ions and balance the whole polyatomic ion together, and this actually speeds up the process. For example, we can see that our product side has 4 phosphate polyatomic ions, whereas our reactant side only has 1, so we can add a balancing coefficient of 4 here in order to balance out phosphate like this. Now this also applies to hydroxide, but there's a little bit of a trick to it. Whenever we're dealing with neutralization reactions, that being an acid and a base that neutralize each other, we know that we're always going to get water, and if we rewrite water like this as HOH instead. Again, we're not changing the chemical formula for water. All that we're doing is writing it differently so that we can see that water is produced from hydrogen, which comes from an acid, which reacts with hydroxide that comes from a base. And then that allows us to see how to balance water more easily. For example, we can see 3 times 4 is that our base has a total of 12 hydroxide ions, and our acid, 4 times 3, is a total of 12 hydrogens, and those 12 hydrogens and 12 hydroxides will combine together in order to give us 12 waters, so we can use the same polyatomic ion trick just with water as well. This particular strategy of grouping polyatomic ions together is especially useful not just in neutralization reactions, but in the broader category of double replacement or double displacement reactions, as they frequently involve ionic compounds that have polyatomic ions. Now, the last set of strategies all concern combustion reactions, which many students will agree is among the most challenging types of reactions to balance, simply because you're going to be dealing with large balancing coefficients. And one strategy that we can use to speed up this process is to determine whether our reaction requires an even or an odd number of specific atoms, specifically an even or an odd number of carbon and oxygen atoms within the reaction. And if we use the first reaction here, we can see, if we look at oxygen, that our reactants can only ever have an even number of oxygen, because oxygen can only be acquired from oxygen gas in this case, because our organic compound has no oxygen present within it, whereas in the product side, because water has only one oxygen, it is possible for us to have an odd number of oxygen. Now, because odd numbers cannot evenly divide into even numbers, it is physically impossible for us to balance oxygen if we have an odd number of oxygens on this side. And we can see that this will be a problem if we try balancing hydrogen. So we have 6 hydrogen here in our reactants, and if we try balancing hydrogen with a 3 times 2 is 6, then we end up with an odd number of oxygen, which will never be able to balance against the reactants. So what we can do in order to make this an even number is we can double all of our balancing coefficients. So instead of having a balancing coefficient of 1 for our organic compound, we can put a 2 here and balance carbon and hydrogen accordingly. So 2 times 6 is 12, so we can balance carbon with a 12 like this. 2 times 6 is 12, so we can add a balancing coefficient of 6, and that way we have an even number of oxygen here, which makes it possible to balance oxygen in the reactant side. So all that we need to do now is count up our oxygen. 12 times 2 is 24 oxygen from carbon dioxide, plus the 6 oxygen from water is a total of 30, and 30 divided by 2 is 15 for balancing oxygen out in the reactants like so. Now, if we compare this algorithm for solving balancing of combustion reactions with the second equation here, we can see that we can actually get an odd number of oxygens on each side, because now, since our organic compound has an oxygen in its structure like this, we can actually have an odd number of oxygen on both the reactants and the product side, which should make balancing more straightforward. So we can stick to our major hydroxide strategy and balance carbon first. So we can put a balancing coefficient of 6 to balance carbon by balancing CO2. We have 5 plus 1 is 6 hydrogen in the reactants. So we can put a 3, because 3 times 2 is 6 hydrogen here. And if we count oxygens, 6 times 2 is 12 oxygen from carbon dioxide, plus the 3 oxygen from water is a total of 15 oxygen, meaning that we need 15 on our reactant side as well. So one of these is going to be the oxygen in our organic compound, leaving us with 14, and 7 times 2 is 14, plus 1 is 15, that allows us to balance oxygen on both sides. So simply by doing a little bit of analysis and seeing whether each side is possible to have an even or odd number of oxygens is a good strategy to help us determine whether we need to double all of our balancing coefficients like so. Now, our last type of chemical reactions are also combustion reactions, but we can see, because of the extra products that are present, carbon monoxide and elemental carbon, that these are incomplete combustion reactions. And even though these look very overwhelming, they actually have multiple solutions, because once again, oxygen and carbon are now found in multiple locations here. So we won't belabor the point of actually figuring out how to balance this. Instead, what I'm going to do is fill in the balancing coefficients one way just so that we can see. So again, we have 6 carbon in our reactants, 1 from carbon dioxide plus 2 from carbon monoxide plus 4 is 6, 14 hydrogen, 7 times 2 is 14 hydrogen, and if we count oxygen, 2 plus 7 is 9, plus 1 is 10 oxygen, 5 times 2 is 10 oxygen, so this balancing coefficient set works this way. But if we were to try a slightly different set of balancing coefficients, which I'm writing in here, if we count our atoms once again, 6 carbon, 3 plus 1 plus 2 is 6 carbon, so carbon is balanced. 14 hydrogen, 7 times 2 is 14 hydrogen, and then we can see that we have 14 oxygen from our balancing coefficient here, and if we count on the product side, 3 times 2 is 6, plus 7 is 13, plus 1 is 14 oxygen, so we can see that both sets of balancing coefficients work. And this, once again, is because carbon and oxygen occur in multiple locations in an incomplete combustion reaction. There are actually multiple ways to balance these, which technically makes it easier as we have a little bit more freedom than what is required in order to balance a complete combustion reaction. This concludes this video on looking at strategies for balancing. To test your understanding of how these strategies work, you can take a look at the practice examples below that work through a number of balancing reactions in escalating difficulty. And once you're done with practice, in the next video we will look at how to convert the written description of a chemical reaction into a chemical equation.